Okay, guys, so I'm up at school and we had some people in today and we talked a bit about non-spontaneous reactions. So that would be a reaction that's step up on the data table. It also has sort of characteristic E naught value that we'll talk about. And I would say probably this is actually a little bit on the trickier side. And so make sure you have one of those handy and even one of these handy. And we'll proceed with our lesson then. So probably 2 lessons to go, this one and one more. And then we'll be finished. And then we'll be testing. I think I said you guys' this test would be on Friday or Thursday. I can't remember. I'll have to take a look. I did send out an email about that. So we'll go with whatever the email says, though. Okay. So I want to make sure that the math guys and the chemistry guys aren't doing the same day for their test. Okay. So so let's take a look. Okay. So let's switch over and we'll talk about a non-spontaneous reaction, and also, I guess, before I finish, why we study them. Like, why would you want a non-spontaneous reaction in the first place? Is there a benefit to that? So I have noticed my hairline is going higher and higher. So it's like, whoa. So anyway, it's all the stress, okay, so let's share our screen. And where are we here? Okay, so non-spontaneous reactions. And let's take a look at what that would be like, sort of thing. So let's see. I just broke something. Oh, it's actually still working. Thank goodness. Okay. All right. So I'm not sure what just happened there. I think I clicked on the wrong tab. So what's happening? Non-spontaneous. There we go. So turn that down. So let's take a look at a reaction that would not be something that's spontaneous. So we'll take a look at, let's say, manganese ions reacting with lead, say. And we tell you that this reaction makes manganese metal. And then also we get some lead ions out of the deal. So where are we? Yeah, lead 2+. Okay, so let's first of all discuss why this would not be spontaneous. Let's take a quick look at that. So we write down our reduction oxidation table. We kind of done that quite a few times in the various videos. And let's take a look at what's being reduced here. So the manganese ions are going from +2 to 0. So that's definitely reduction. And then the lead metal is being oxidized into lead ions. So this makes it pretty easy for me just to say, well, manganese ions are on this side, they're being reduced. Now I just got to find my lead. So my manganese ions, if you're looking for them, are at -1.19. And the lead reaction, where lead metal is being oxidized, is at -1.3. So it's actually above. And lead is there. So according to this reaction, it's saying that it's happening, they're reacting. But if you notice where their placement on the table is, this actually would be a step up reaction. So the thing that's being reduced is actually lower than the thing being oxidized. And we said that that's not spontaneous then. This should not happen. So we'd have to figure out why is this happening, and we'll address that in a bit. But really what's happening is the lead is being turned into lead ions, and you're getting 2 electrons removed, so that is oxidation of lead. And then the manganese is taking those 2 electrons and turning into manganese metal. So once again, that's pretty clearly not something that should happen on its own. And the reason it shouldn't happen, in case you're like, why shouldn't that happen, is that if you started to make lead ions here, they're actually higher up on the oxidizing agent side of things, so they would immediately get reduced again in this reaction, unless something else was going on here. Okay, so that's sort of the gist of what we call a non-spontaneous reaction here. And once again, there are reasons why you would want to do this, and how, and more or a better question would be, how do you do this if it's not spontaneous? So let's take a look at the two types of situations we can come across here. So the actual process is referred to as electrolysis. And so lysis meaning to split, and then electro obviously do electricity. So basically using electrons to split things to cause certain reactions to take place. So electrolysis can take the form of two different types. One is with a molten salt, and the other is with a with an aqueous solution. Electrolysis with molten salts is actually fairly straightforward. The aqueous solutions, they're really not fun. In fact, the kids that were here in class today, they were crying afterwards. It was very sad. I really felt for them. Anyway, here we go. So let's take a look at a molten salt. So what would that look like? Okay. So the first thing is we have two electrodes sticking in, and we'll make one of these electrodes carbon and the other one platinum. And then what we do is we attach the electrodes to a DC power source. So what would that mean? Well, the DC power source is a battery, so it'd be like having a Duracell battery or something there. Or you could think of it from the previous videos. Remember the two beakers we were drawing, electrochemical cells? That's what a battery is. So really the DC power source is a battery, electrochemical cell, voltaic cell, galvanic cell. So we have a battery up here. And then I'm going to make the battery have the negative end on that side, the positive end on this side. And then we have a molten, let's do molten here. Let's do molten salt, okay? So I'm gonna go draw some kind of liquidy thing in here. And we're gonna say this is molten. Let's make it molten. Magnesium. Magnesium iodide. Okay, so molten magnesium iodide. Okay, so first of all, we have to understand molten is really, really hot. So that means you have melted the magnesium iodide, not dissolved it, but melted it. So it's in liquid form. And what that means, it's so hot, it would be, there was a joke in there somewhere. Sorry. It's so hot. How hot is it? It's so hot that there'd be no water present. So the water would be all gone if there was any water there. So just basically a salt, you melted it. And then what would happen is these ions would be floating around because they're no longer a solid, but they still would be kind of connected to each other. So you'd have Mg2 plus, and you have some I minuses. And then what happens is the battery pumps electrons out of the negative end and sucks them out for the positive end. So electron flow is flowing that way with this particular battery. If you had switched the positive and negative ends, it would just it would flow the other way. So you're pulling electrons away from the platinum, which means that you're stealing those electrons. So basically you're oxidizing there. And then at the carbon site, you're giving it electrons, so you're able to reduce at that site. So really the electrons always flow from anode to cathode. And we learned that in other videos. And now we sort of have a sense of what's going on here. But let's write a table out again, just to take a look at what could be reduced and what could be oxidized, okay? So if I look at this scenario, I've got magnesium ions. Well, they can definitely be reduced. You can see them on the table pretty easily. They're down at, where are we here, magnesium, negative 237 if you're looking. And the iodide's quite high up, kind of a little bit past halfway, I guess, at 0.54. So the iodide is up here. Okay, so relative to each other, you can see this is a step up reaction. So this reaction should not take place on its own. And in fact, it won't take place on its own. So there's something helping it do this. So what is it that's helping this cell react this way? Like, why would it react this way? And the reason for it is the battery. The battery is basically forcing electrons into the carbon and out of the platinum, and this is causing reduction and oxidation. Now, the one thing I haven't addressed, and you probably have been thinking about this, is why am I using carbon and platinum here? Like what is the point of that? Because in the other cells, we kind of made the electrodes out of the metals that we were studying. And the reason we're doing it here is the carbon and the platinum, I'll write this up here, carbon and the platinum electrodes, they are what we call inert. And what that means is they are electrodes that are not going to react in the reaction, but they are going to allow for electrons to move across the surfaces of them. So they do allow electrons to move from one side to the other, but they are not being reduced or oxidized in the process. It just happens to be they're not very good at being reduced and oxidized. So if you sort of think about that, they would have a special place on the table, relatively high or low, depending on what's trying to happen to them. You don't need to know more than that, other than you can basically ignore them. So carbon and platinum can be basically ignored here. Okay, so what's going to happen? Well, the magnesium is going to undergo reduction. So it's going to go that way. And it takes 2 electrons to do that. And it turns into magnesium metal. Okay, so where would that happen, do you think? Do you think that would be happening at the carbon or the platinum electrode? Well, reduction and oxidation, you can use that silly little saying, an ox cared, right? So anode, oxidation, okay? Reduction is the cathode, okay? So what we know is the magnesium ions are going to move towards the cathode, okay? And they're going to undergo reduction. So you would start to see, well, you may not see it, because I'm thinking at this temperature, the magnesium metal that's forming could also be in liquid form. I actually wouldn't know this, but there would be magnesium forming, like the actual metallic form of it. It just might not be a solid at that point. So it would all depend on the temperature of these things. You're not expected to know that, but you are expected to know that magnesium would form. And of course, at the anode, you have the oxidation. I think I should use different colors. There we go. So we have the oxidation of the iodide, which is going to turn into iodine, and 2 electrons. Get 2 of those. So what's happening here is that's moving over there, and you're getting iodine. And at that temperature, I believe the iodine will sublime and will be turning into a gas at that high of a temperature. So you might actually see bubbles forming in the solution at that point. Okay, so there we go. So that's a non-spontaneous reaction, one that does not happen on its own, unassisted. And I'm going to move on to just one more example of that type, and then we'll move on to the worst of the worst. Sounds ominous. So let's take a look here of 2 electrodes. Let's make it copper and platinum. And my battery here. DC, put that the negative end, the positive end. And then let's go molten again. So molten. And we'll make this, what would be a good chemical here? Let's make this tin bromide. Okay. Okay, so pause the video, see if you can find out what the anode and cathode are, see if you can see the flow of electrons, or determine the flow of electrons, and what's being reduced, what's being oxidized, and let's go from there. But I really would encourage you to pause it, see if you can do it on your own. Okay, so let's see if you paused it. All right, so I know floating around in here would be my tin ions. I'd have some tin ions floating around, and I'd have some bromide ions floating around. Okay, and the question is, would the tin get reduced? Would the bromide get reduced? You know, what's going to happen here? So looking at the data table, I can see tin 2 plus on. I'm going to use red for reduction here. I'm going to use tin 2 plus on that side. And so I can definitely see that. at negative 1.4, or 0.14. And I've got bromide up here, and that's at 1.09. And you might think, okay, well, there we go. We got reduction in oxidation taking place. Pretty clear what's happening. Not spontaneous because it's step up. But if you look a little closer at the table, you actually can see that tin 2 plus is on the right side also. And so tin 2 plus is at 0.15. Okay. Alrighty, so now we got to do some thinking here. So on the left-hand side, the only thing that can get reduced is the tin 2 plus. So that's kind of what has to get reduced there. And then on the oxidizing side of things, you've got bromide and tin 2 plus. But the thing that's the stronger of the two is the one that's lower down. So that would be the tin 2 plus. So the tin 2 plus must also get oxidized here. So here we have a species that can get reduced and oxidized, and does actually in this question. So what would happen is the tin 2 plus would move towards both electrodes, but let's determine which electrode is which. So electrons flow out of the negative end and are taken from the positive. So we have electron flow. And we know that electrons always flow from anode to cathode. It's alphabetical. That's how I remember it. And we know that reduction is happening at the cathode because an aux carried. So the tin 2 plus would be moving here. And then the tin 2 plus would also be moving here. So you couldn't really get that part wrong. What you could get wrong is what forms at each electrode. So at the reduction site, the cathode, the tin 2 plus is turning into, you're giving it 2 electrons. So it's turning into tin solid. So really this is going to form tin solid. And once again, that could be a molten form at this point. We're not too sure, but you would get tin solid. Sorry, you get tin metal forming, not tin solid, but it could be in liquid form. And then at the other site, we have tin 2 plus that's being oxidized into tin 4 plus and 2 electrons. So at this site, we wish you would get tin 4 plus, a different oxidation state for the tin. Okay, so that's maybe kind of confusing. So I'm going to make this actually 2 videos, but I want to start you off with this just to make you kind of think about it. And so this is electrolysis for solutions. Okay, so we're going to look at a solution now, and I'm going to set it up for you so you can give it some time to think about what is going on here. So let's take a look at, I should probably just move that down actually. So let's give ourselves some room here. So let's take a look at this big beaker. You guys ever watch the Muppets? I liked Beaker a lot. He was pretty cool. Okay, so there's our battery there, okay? So make this carbon, make this platinum, and let's put the negative end here, positive end here. And now what we're gonna do is we're gonna make this a solution, so not a molten situation, but 1 molar, and let's use strontium fluoride. Okay, strontium fluoride here, okay? And so once again, try to set yourself up a little reduction table and an oxidation table. And once again, try to answer this on your own. Try to see what you think would happen here. Which one's the anode? Which one's the cathode? Where is reduction happening? Where's oxidation happening? What are the products being formed here? And my second video will sort of address this. I just want to make sure I don't make this one too long. Okay, so I'm just going to stop sharing.